All right, so today we're going to take a look at the second fundamental theorem of calculus. And so what we're going to do here is we're going to start off, and I've defined a function in example number 1 here. I've defined a function g of x, and g of x is the integral from 0 to x 2t dt. And this is a function defined by an integral, so g of x is an area function. Because remember, an integral finds us the area between the x-axis and a given curve. So g of x is now an area function. So you'll notice we have x's and t's in here. I don't want you to worry so much about that at this point. We'll talk more about these later. But so g of x is defined as the integral from 0 to x of this other function 2t dt. So I'm going to start by graphing the function f of t equals 2t. Well, that's just a straight line function. It starts at 0. It goes up 2 and over 1, up 2 again, over 1 again. And if I'm going to go from 0 to x, let's go up 2 and over 1 again once more. That'll get us right about there. And so that graph would just keep going and going and going, just like that. It would also go down to the left, but we're only going to talk about positive values here. So the first thing I want to do is know that this is the graph of what's next to the integral. F of t equals 2t. And so what I want to do is I want to find some values of x. You'll notice I'm going back to x, which means I want to solve for g of x. So I want to solve for g of 0 here. So the first thing I'm going to do is I'm going to take and I'm going to plug in 0 into the function g. Well, what does that do to the right side of my integral? It now has the integral from 0 to 0 of 2t dt. And what this is saying is find the area from 0 to 0. Okay? So I know that the area from 0 to 0 is just 0. Okay? So at 0, g is 0. That's the area at 0. Then we go to g of 1. So I do g of 1. That is now the integral from 0 to 1 of 2t dt. Now if you go look at my graph, I can come over here. I can draw at 1 here. Oops. Pardon me on that one. Wrong spot here. This was 1 right here. So if I draw from 1, I would have this little triangle right here. I want the area of that triangle. That's what this integral is now asking for. Well, the area of that triangle is 1/2 base times height. So the base is 1 times 1/2 is 1/2 times the height of 2. That's 1/2 times 2, which is 1. So my function g at a value of x equals 1, the area is 1. Okay? So again, that's what we're calculating here. We're calculating areas given a function g of x. Okay? Let's go to the next one, g of 2. And by the way, we could also do these using the fundamental theorem of calculus, f of b minus f of a. We could do that as well. But because these are nice little triangles, we're going to stick with the graph. This is the integral from 0 to 2 of 2t dt. So now I go over to 2, and I'm looking at all of this yellow area highlighted in here. So that's going to be 1/2 times the base of 2. So 1/2 times 2 is 1, times the height is 4. And then we would do this one more time. We would do g of 3, and that becomes the integral from 0 to 3 of 2t dt. And again, you could do that with fundamental theorem, use t squared as your antiderivative. But we've got our graph here, and you can see that the base is 3, the height is 6. 3 times 6 is 18, divided by 2 is going to give me an area of 9. Okay, so all it is a function that's defined as finding the area under the curve. Okay? Now, how do I actually use the second fundamental theorem of calculus? That's just a function defined as an integral. How does the second fundamental theorem work? It says, assume your function is continuous on some interval. Then the area function, just like we saw before, g of x equals a to x. Okay, x is a variable. A is a number. Okay, that's all this is, some number. This function is an antiderivative of f of x. Now that's going to sound weird for a minute. We've got g of x, we've got f of t, we've got f of x, and they're saying that g of x is an antiderivative of f of x. So let's see how this works. When I take the derivative of g of x, that becomes g prime of x. Okay, we know that notation. I take the derivative of g of x, that becomes g prime. When I take the derivative of the right side, so I'm actually going to start right here. The derivative of the integral from x to a f of t dt, that equals f of x. What happened in there? The only thing that happened is if I take the derivative of an integral, I plug in this x into the function, and I'm done. Now there's a little more to it on the fundamental theorem, but today that's all we're looking at. What happens if my integral goes from some number to x? If I want to take the derivative of that, that means I plug in x for t, and I get f of x. I'm done. There's no plus c. I don't worry about any of that stuff. So what we are saying here, therefore, is that g prime of x is equal to f of x. Those two are the same. Okay? So if I wanted to take, for instance, if I defined g of x equals 0 to x of 2t dt, well then g prime of x says take x, plug it in here for t, and g prime of x is 2x. And therefore, g of x, I want you to think about g of x now. Now, right now, g of x is defined as an integral from 0 to x 2t dt. So if I find the derivative is equal to 2x, which means the original function g of x had to be the function x squared. Because x squared is the antiderivative of 2x. That's why it says that the area function g of x is an antiderivative of f of x. There's your little proof right there. Okay, little algebraic showing there. G of x equals the integral from 0 to x 2t dt. To find the derivative, all I'm going to do is take that value of x, plug it in for any variables. That function is the derivative of the original function g of x. Okay? And again, there's a lot more to the second fundamental theorem. We will talk more about that on another lesson. Let's take a look at this example. Kitty Cat Kong in the helicopter over here on the right. You can see Kitty Cat Kong. Kitty Cat Kong's altitude in feet is given by this function. H of t equals 0 to t. There's my integral 0 to t, 64 minus 12u. These variables will not ever be the same in this type of function. T is defined as the upper limit. U is the variable of integration right now, where t is measured in seconds. When does Kong stop going up and start coming down? Well, Kong stops going up and starts coming down. Think about that. When my derivative is equal to 0. Because if my derivative is positive, Kong's going up. If my derivative is negative, Kong's going down. So when my derivative is 0, Kong has stopped going up and is starting to come down. I need to know when is h prime of t equal to 0. That's the answer I need. How do I find h prime? Well, we're going to do that. We're going to use the second fundamental theorem of calculus. h prime of t is equal to, and remember, all I do is I take that variable, I substitute it for the variable in the equation. That's going to be 64 minus 12t. Remember, I'm not doing an antiderivative right now. All I'm doing, the second fundamental theorem of calculus says, all you have to do is take that top variable and plug it in for the variable in the equation. I now have a brand new equation that I can set equal to 0 because this is my derivative. 64 minus 12t. If I add 12t to both sides and solve this, we're going to end up with t equals 64/12, or maybe 16/3 seconds. Now, I could check that using a number line, or we also called it a, oh my gosh, my mind's going blank right here. But I could check this. I could plug in numbers that go from 0 to 16/3. Okay, this is my derivative function, h prime. So just like we did last semester, we could plug in values and verify that Kitty Cat Kong was going up, that the derivative was positive from 0 to 16/3, and now the derivative is negative from 16/3 to infinity, or whenever Kitty Cat Kong hits the ground. And therefore, we know that 16/3 must be a max. Okay? All right, so our next one is a familiar one as well. It says, if f of x equals 3 plus the integral from -2 to x sine of pi t squared over 8 dt. Looks like a nasty equation, but let's see what's happening here. Write an equation for a tangent line to the graph of y equals f of x at the point where x is equal to 2. Every time we do one of these, ladies and gentlemen, I talk about the fact that we need a point and we need a slope. I'm going to start with the point, just like I always do. I need to plug in -2 for x. I need f of -2. So if I plug in -2, that's going to be 3 plus the integral from -2 to 3 of sine of pi t squared over 8 dt. Okay, so I need to actually plug that in. Now, take a look here. I just realized I made a mistake on my upper integration. I'm finding f of -2, so it's equal to 3, the original number in front, plus the integral from -2 to -2. There we go. All right. Now, here's the nice thing about this. I know that the integral from -2 to -2 is just going to be 0. So f of -2 is just going to equal 3. Okay? So there's my point. Now I need a slope. Well, a slope comes from a derivative. So I need f prime of x first. So I go back to my original equation and I look at the 3. What's the derivative of 3? That's 0. And then for the derivative of the integral, I'm going to take that value of x and I'm going to plug it in for t again. So my derivative is 0 plus, or just plus, sine of pi x squared over 8. That's my derivative. Now I plug in -2 again. I get f prime of -2. So I pop that in. This is sine of pi times -2 squared all over 8. -2 squared is 4, and 4 over 8 is 1 over 2. So what I'm really evaluating now is sine of pi over 2, and I know that sine of pi over 2 is 1. This is my slope. So my equation would then read y minus y1, which is 3, equals m, which is my slope, times x minus x1, which is -2. So I could just say that this is y minus 3 equals x plus 2. All right? Number 4. Given another area function, a of x equals the integral from 0 to x f of t dt, answer the following questions. I would encourage you to turn off the recording, try answering these on your own, see what you can answer. We've talked a lot about derivatives and increasing, decreasing, all that kind of stuff. So, when is a increasing? Well, I know that any function is increasing when its derivative, a prime of x, is greater than 0. Now, I can't do this on this function because I don't know what this function is, but that's what I would need to know. When is a of x increasing? When its derivative is greater than 0. When does a of x have a minimum? Okay, so think about that one. For a graph to have a minimum, its derivative, so again, when a prime of x, to have a minimum, that means you had to go decreasing to increasing. So my derivative goes negative to positive. When is a of x concave down? Okay, concavity has to do with the second derivative. When a double prime of x. If I'm concave down, my second derivative is less than 0 or negative. When does a of x have a point of inflection? Again, this is second derivative. When a double prime of x goes positive to negative or negative to positive. Okay, so we can still answer the same questions based on what we talked about last semester. All right, that's it for this one.